There are three common uses of a rotation matrix. The first is to represent an orientation. The second is to change the frame of reference of a vector or a frame. And the third is to rotate a vector or frame. To demonstrate these, I will use these three coordinate frames representing the same space with different orientations. To help you visualize these frames in 3 dimensions, I'll use my handy Tinker Toy frame. This is the z-axis of the frame, this is the x-axis, and this is the y-axis. So initially, I'll orient it aligned with the frame S, and then I'll rotate by 90 degrees about the z-axis, and then I get the frame B. And then if I rotate by minus 90 degrees about the y-axis, I get the frame C. As we saw in the previous video, we can represent C relative to S by writing the coordinate axes of C in S coordinates, yielding the rotation matrix RSC. If we write the coordinate axes of S in C coordinates, the resulting rotation matrix RCS is just the transpose or inverse of RSC. To demonstrate a change of reference frame, consider the rotation matrix RBC, representing the orientation of frame C in frame B coordinates. If we want to express the C frame in S coordinates instead of B coordinates, we can perform the matrix multiplication RSC equals RSB times RBC. By pre-multiplying RBC by RSB, we've changed the representation of the C frame from the B frame to the S frame, as we can verify by inspecting the rotation matrices. You can remember the change of reference frame operation by a subscript cancellation rule. If the second subscript of the first matrix matches the first subscript of the second matrix, they cancel each other, leaving the 2 remaining subscripts in the right order. We can also change the frame of reference of a vector. Let PB be the position of point P when expressed in B frame coordinates. To express P in S coordinates, we can pre-multiply PB by RSB to get PS. This operation again satisfies a subscript cancellation rule. The final use of a rotation matrix is to rotate a vector or frame. For example, it is apparent that the B frame is obtained from the S frame by rotating the S frame about the ZS axis by 90 degrees. Thus, we could consider the matrix RSB as an operation that rotates about the z-axis by 90 degrees. If we pre-multiply a vector PB by this rotation operator, we just get a change of reference frame to S coordinates, as we saw before. But if the vector is PS in S coordinates, then there is no subscript cancellation, and instead we get a new vector P'S obtained by rotating PS by 90 degrees about the ZS axis. The vector has been rotated, but it is still represented in the original frame S. We can also rotate the frame C by pre-multiplying or post-multiplying RSC by the rotation operator R. If you pre-multiply by R, the rotation axis is interpreted as the z-axis of the frame of the first subscript, S. You end up with a rotated frame C prime, still expressed in S. If you post-multiply by R, the rotation axis is interpreted as the z-axis of the frame of the second subscript, C. You end up with a different rotated frame, C double prime, still expressed in S. In summary, a rotation matrix has 3 uses: representing an orientation, changing the frame of reference of a vector or a frame, and rotating a vector or a frame. In the next video, we will learn how to represent the angular velocity of a frame.